you've assigned things correctly. Okay. All right. So we talked about some basics for assigning expressions using our slides. Let's do an example problem wherein I actually show you how to, assign these expressions. What we're going to do is we're going to take a simple pipe flow problem, and we are going to assign a turbulent velocity profile at the inlet. The function of it looks like this. So Umax will be a value that I assign, and the maximum radius will be a value that I assign. This radius will be computed based on the coordinate location or the spatial coordinates at the particular flow boundary. Okay, so we'll assign the turbulent velocity profile at the inlet. We'll also assign a transient pressure at the outlet, right? A pressure condition that varies with time. We'll also use an expression to assign a volumetric heat source in one of the fluid volumes in our domain. And then we'll use some expressions for post-processing. So I think if we do all these things successfully, it'll give you a good comprehensive idea of where all you can use expressions in your own problem. Okay. So let me go ahead and show you the geometry. So you should be seeing my Fluent window on your screens now. Okay. This is a simple example pipe. I didn't check the dimensions. I just, built something arbitrarily. And I've loaded this in Workbench. I've already opened the file to save us some time. The mesh is quite coarse again, because I don't want to spend too much time with the computations. But basically, one of these zones is going to act as a heat source. There is an inlet on one end and an outlet on one end. Okay. So the first thing I'm going to do is I'm going to assign this as a transient case, because remember, we were going to vary the pressure at the outlet with time. Okay. So let me go ahead and do that. I'll also go ahead and assign the units for temperature as Celsius. Okay. And then I'm going to go ahead and turn on the energy, because I can't assign a heat source if the energy equation is not turned on. Okay. Now, I generated a default mesh in Fluent meshing without actually opening it. So everything is by default considered a solid. So let me go ahead and make all the domains fluid domains. Okay. So this particular domain is going to be my heat source zone. Okay, so I'm going to assign a user heat source for this particular domain using an expression. And for this, I'm not going to use the expression editor. I just want to demonstrate an example where you can directly enter the expression in the field itself. The material is air. I don't want to, bother changing it. Let me just go ahead and assign a source term over here. So this tab becomes active. And we can come to the energy field, click on edit, increase the number of energy source to 1. And then it is asking us what type of assignment do we want in this case. Usually what we will do is, we will enter a constant value. We know the volume of the domain from our CAD. So we divide the total energy by the volume, and then we'll enter a watt per meter cube value. That's what we usually do, right? So what if we didn't have to know the volume of the particular zone in advance? What if we could use an expression to just simply assign the overall heat source and then divide it by the volume? So that's what I'm going to go ahead and do. I'm going to click on expression and say I want this zone to have an overall heat production of 20 watts. Okay. So what I'm going to go ahead and do is I'm going to put in 20 watts divided by the volume of this particular zone. So you can see that the name of the zone is heat zone. Okay. So what I'm telling in this expression for Fluent to do is divide 20 watts by the volume of this particular fluid domain. And I'm entering this expression directly in this field. Before I erased the other units that were by default present, you could see that Fluent was giving me a message, invalid syntax or incomplete expression. That's because it was not complete. Once you have the correct complete expression in the field, it's not going to give you any more errors. So you can just simply go ahead and hit OK and then apply. Okay. All right. So we've done this portion here. Now, whatever other expressions we are going to write, we are going to use the expression editor. Before we do that though, let me go ahead and convert my inlet to a velocity inlet. We'll come back to it later, and then let me assign my outlet as a pressure outlet. Okay, all right. So now we can get started with writing all our expressions in the expression editor. So this is the outline view, and this is where you can use or enter expressions in the editor. So just right click on it, go ahead and hit new, and this opens the expression editor box. Okay. So remember how I said that I want the pressure at the outlet to be a transient function? So I'm going to vary it with time. So let me just put this some name of the expression, right? So any name. This is just an assignment for the actual expression that you write so that you can select it from drop-down menu. So you could make it P outlet, you could make it P out, whatever you want. So this is the definition is where I write the expression. Now, say for example, you're completely new to writing expressions, you don't know how to start. You can have some idea of how to use the functions and variables by looking at these drop-down menus over here. So I'm going to enter a conditional statement over here. So I could go to conditional, and then I could click on if. And it gives me the overall syntax of an if statement, right? So there is the condition first, and then what happens if the condition is met? What happens if the condition is not met? Okay. So if you are completely brand new to writing expressions, I would say use these drop-down menus quite often. So I'm going to say that if my time is less than 0.5 seconds, and seconds will go in square brackets, remember the units go in square brackets, then I want my pressure to be 0 Pascal. If not, then I want my pressure to be 100 Pascal. Okay. So what I've basically done is if time is less than 0.5 seconds, my gauge pressure at the outlet should be 0. If not, then it should be 100. Okay. So no more errors, no more messages. So this is okay. I'm going to go ahead and hit okay. I also get the mass flow rate at the outlet. So let me go ahead and enter another expression over here. And as soon as I click on M, it'll give me a bunch of options to choose from. Okay, so I could go with mass flow, or if I was writing some other kind of expression, maybe I'm going to use a reduction or an averaging function, then I could also go with mass flow average. But in this case, I'm simply going to choose mass flow. And then again, we are going to enter the location where I want the mass flow. So I want it at the outlet. Okay, I'm going to plot it later on when I run the simulation. All right. Now, another expression that I want to add is the pressure drop expression. That is quite common. We do it for internal flows all the time. The difference in static pressures between the outlet and the inlet, right? I don't want to do it manually. I don't want to, compute the outlet pressure and then the inlet pressure and then subtract it manually after my simulation is done. So what I do is I just put in pressure drop over here. And think about it the way you would go about manually extracting this information. What do? We take the mass flow average at the outlet of static pressure and mass flow average of static pressure at the inlet and then subtract, right? So we're going to do the same thing in the form of an expression. So we'll do static pressure at the outlet minus, let me go ahead and copy the same expression over here, Control C, Control V, and I'm just going to change the name from outlet to inlet. Now, the other thing that you may be interested in is, say, for example, you have a lot of flow boundaries in your problem, and you don't remember the name assignments of individual boundaries, right? In this particular case, I marked it as outlet and inlet. But what if you had a couple of different boundaries that you were working with and you don't remember the exact names that you assigned? You could also just look at locations, and you could look at particular cell zones or boundary zones. So now you know the exact name of the location that you want to compute your functions at. Okay, so this can be another good way of making sure that the name in between the quotes that matches with what you have assigned in your flow domain. Okay. All right. Okay, so time to enter the turbulent velocity profile at the inlet. There were two values that I was supposed to assign, the maximum velocity and the maximum radius. So let me quickly go ahead and assign those values. So this is just a variable that has an assignment of 0.5 meter per second. And another one for the maximum radius. I have this value known from my CAD geometry. What is the maximum radius at the inlet? So that is 0.005 meter. Okay. All right. And we calculate another expression, which is the radius of the inlet. Now, this is what makes it a multi-valued expression, because remember, at the inlet boundary consists of a face, okay? It consists of multiple faces from the mesh that is used to describe that particular boundary, okay? So at every face center, your coordinate is going to be different. Your coordinate of X, Y, Z is going to be different. So how do you calculate the radius at any point? You use the same mathematical expression that you would when you're doing, hand calculations, right? So it's going to be x squared plus z squared whole square root, okay? So if you look here, the inlet, if I go ahead and display the inlet, it is assigned with the x and z axis, okay? So that's why when I write the expression for radius, I'm going to use those two coordinates to calculate the value. And then the square root of this entire function. Okay, the same thing that we would do, when you're just calculating the radius of any circle. Okay, so, all right. So once I have the individual components of the overall turbulent velocity profile ready, I can finally go ahead and build my velocity inlet. So the entire expression was Umax. And because we have already entered an expression in the name of Umax, when you type in U, there is an automatic suggestion of choosing one of the predefined expressions. Okay, so if you've already defined an expression, that also shows up as a suggestion. So you have Umax into 1 minus radius, something that we just defined, and max radius divided by max radius, 1 divided by 7. So this is the overall function that I wanted to assign at my velocity for assigning the turbulent velocity profile, okay? So 3 of these values, 3 of these variables in this expression, they are actually predefined expressions. So you can use multiple expressions to calculate derived variables. That's the beauty of using an expression manager, okay? All right. So I have 7 expressions defined over here. If you hover over these, right, they will give you some more information about what you've defined. They'll tell you whether it is single valued or whether it is constant valued. It'll also give you the dimension, the final SI dimension for the expression so that you know where all it can be assigned, okay? So now that we've defined all these expressions, let's actually go and assign it. We never did that. So we go to inlet velocity. Where you would put down the velocity magnitude, you instead click on the drop-down menu, and it shows you only those expressions. Fluent is very smart, right? So it shows you only those expressions that are dimensionally consistent with velocity. So we want to assign this function over here. And I'll put some arbitrary number for temperature. And then at the outlet, instead of defining a constant value for gauge pressure, again, see, only the pressure expressions are shown in the drop-down menu. So I'm going to go ahead and use P outlet. Okay, excellent. So now that I've assigned all these values over here, let me use the expressions and report definitions, because we talked about how expressions can be used for post-processing as well. So say, for example, you wanted to plot an expression while your iterations are being solved. You can simply go to report definitions, right click, click on new, and then here you have something called expression. So let's go ahead and plot pressure at the outlet, because I want to see whether it varies with time as we intended. Okay, and let's print to console. This is going to report file, report plot, and it's going to print to console. And then we are also going to plot the pressure drop. Okay. Excellent. So I can then go ahead and initialize this guy. If it takes a lot of time, I also have a solved case ready. Actually, let me show you the solved case, because the number of cores on my machine is limited. I have 2 Fluent sessions open. Okay. All right. So the hybrid initialization is done. Hopefully it doesn't take too much time. Let me just put this number of time steps just to 5. I had a Fluent session open for the very same reason. Sometimes when you have too many applications open on your machine, it's tend to freeze. Instead of waiting for that to compute, because I feel like I had 2 sessions open and one had more compute cores than the others. But okay. So in this particular case, I already solved the case, and I want to show you some things in terms of post-processing, okay? Remember, we had a velocity profile assigned at the inlet. So because we have a predefined expression in this particular setup, when you open contours after your simulation runs for a few iterations, you will automatically see an additional option of looking at the contours of expressions, okay? So under expressions, if you look at the drop-down menu, there are only 2 expressions that had multi-valued solutions, right? So all other were single valued because there was just one constant return value. But for velocity inlet and radius inlet, because they were varying with the spatial coordinates, you can actually plot them on a field. So that's what we are going to do. We are going to look at the velocity at the inlet. And if you look here, instead of a constant value, say, for example, 5 meters per second or 6 meters per second, you actually see a variation from the perimeter of the inlet to the interior, depending on the radius that was calculated, okay? So this is what expressions can do in terms of giving you additional ability of manipulating your boundary conditions. The other thing that I also want to show you guys is that because we had the report definition for the pressure outlet, we can actually go ahead and look at the outlet plot of how the pressure varied. So say, for example, if I calculate this for another time step, you can see that the pressure varied based on the expression we assigned. So up till 5 seconds, it was supposed to be 0 gauge pressure at the outlet. And then after that, it was supposed to be 100 Pascal at the outlet, right? So right at the 5-second mark, you can see a jump, and that shows you how the pressure varied, and we were able to assign a transient value to this particular flow boundary. Similarly, you could also plot other things like pressure drop. I think in this particular simulation, I did not set up an additional expression for pressure drop. But if you wanted to see how it varied with different iterations, you could plot it in a similar fashion. All you would need to do is add another expression to your report definition. Okay. Now, this particular plot is visible if you add it to the report definition, but you could also just go to your expression editor and use this plot functionality. Sorry, I closed it. But you could also just look at this value over here to see how your pressure is varying with time, because that's the expression that you've entered. So if you want to make sure that it has been assigned correctly, you could use either this or you could use the report definition. Okay, so whatever values you've computed, you can, come here and look at it. Now, remember, I told you that only single valued expressions can be calculated over here. So say, for example, your simulation has run for a few iterations, and now the data is associated with each and every cell. You can come to the expression editor and hit this green refresh button, and it'll give you the current value at this particular time step. So at this particular time step, your pressure drop between outlet and inlet is around 99 Pascal. So you run it for a few more iterations, few more time steps. This value may change depending on how the flow progresses. So all this extra capability is available to you through the expression editor. So make sure that you're able to use this for your own problems. Okay. So let me go back to my PowerPoint presentation so that I can just summarize everything that we learned today. So Fluent expressions and the expression manager can be used to easily customize your case setup, especially if you have variable boundary conditions, cell zone conditions, material properties. You can do that without needing to use user-defined functions or any complex type of programming language. I also added some useful expressions in this summary slide. So these are the most frequently used expressions for medium range CFD simulations. So if you guys want to pause at this slide later,